Okay, in section 5.1, we're going to be taking a look at what's called the area problem. So the title of the section is Area and Distances, and we'll eventually see how this relates to the notion of distance. But here's what I've got. I've got a function f of x. It's continuous and non-negative on a finite closed interval from a to b. Now, non-negative means I'd be okay if it dipped down and touched the x-axis, but it's not allowed to go below the x-axis. We're not going to have any negative y values here, okay? For the interval from a to b, it's always the case that we list our interval notation, of course, from left to right. I happen to have drawn this so that a is a negative number and b is a positive number. That's not important. It can be any interval from a to b. A is the left endpoint, b is the right endpoint. Okay, and what we're trying to do then is calculate this area that I've shaded in yellow. I don't know how well that shows up here. I didn't want to shade it in the sort of reddish orange that I'm using because I'm going to be writing on this region in a moment. But I'm trying to find the area between the curve and the x-axis over that interval. Okay, so the x-axis is like the floor, the curve is the ceiling, and I've just drawn in walls at A and B, and we're trying to calculate that area. And this is kind of complicated because I don't have a name for that shape. It's not a rectangle, it's not a circle, it's not a triangle or a trapezoid, so I don't have a geometric formula for that. So what we're going to do is we're going to develop this four-step process for finding the area. The first three steps are going to give us an approximation. The area is about this. And then the fourth step will take that approximation and turn it into the exact answer. Okay. Now, it's going to take us a while to do that, and there's a lot of vocabulary involved. But that's our goal. I want to know the area of that yellow region. Okay. And the first step in my four-step process is I am going to chop. Okay. I'm going to chop things up into little pieces. The idea here is sometimes it's better to have a whole bunch of little problems than one big honking problem. Okay, so I'm going to take the interval from A to B, and I'm going to chop that into a bunch of different pieces. Okay, so a partition, this is an important vocabulary word here, a partition of AB is a set of n plus 1 endpoints. So A will equal x, and I'm going to put a subscript of 0 there, which will be less than x1, which will be less than x2, dot, 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 which will be less than x sub n, which will equal b. Okay, so essentially I'm taking A, which is my left endpoint. I'm calling that x with a subscript of 0. And then I'm putting an x1 and an x2 and an x3 and an x4 and an x5. I'm just going to put a dot, dot, dot. Okay. B is going to be my last one, x sub n. Okay. So n is sort of a variable here that's taking on integer values. That's going to represent the number of pieces into which I have chopped things. Okay. Now notice, I said we've got n plus 1 endpoints here. That's because I started my index here at 0. So 0, 1 through n, that's n plus 1 endpoints. But that actually breaks this interval into n subintervals. If I just take a look here, just right here, going from x0 to x2, I can see that's 2 subintervals. But I have 1, 2, 3 endpoints because I have the left endpoint and then the 2 right endpoints. Okay. So if I want to break things up into n pieces, I will have n plus 1 endpoints. So it's a set of n plus 1 endpoints where A is the very leftmost endpoint, B is the very rightmost endpoints, that breaks the one interval AB into n subintervals. So I'm going to chop this up into a bunch of pieces. Now, when I do that, that's going to induce a chopping of this area into a bunch of little pieces of area as well. Okay, so that breaks this up into a bunch of little strips of area. Okay. Now, there's nothing to say that I have to make it so that all of these little strips of area have the same width. In other words, the lengths of these subintervals don't all have to be the same. In fact, I purposely drew it so that this one is a little bit shorter than the ones on either side of it, because that's totally legal. The point of the partition is to chop this up into sub-pieces. Now, strategically, it might make sense to make all of the subintervals have the same length, which would make all of these little strips of area have the same width. What's kind of nice about that is that's just one number to keep track of. That's the length of every single subinterval and the width of every single strip of area. So a regular partition is one in which the endpoints are evenly spaced. And for our purposes, it's generally going to be good strategy to use a regular partition. So in this case, the length of each subinterval is the same. So I'm just going to call that delta x. And delta x, if I'm chopping this up into n pieces that are of equal length, it's just going to be the length of the interval divided by n. But the length of the interval is just the right endpoint minus the left endpoint. So if I use a regular partition, all of my subintervals will have a length that I can call delta x. Okay. And that means that all of these pieces here, all of these strips, will have the same width. So I'm going to make an executive decision that we're going to use a regular partition. So I'll draw this in. Now, this is not meant to indicate that we're using exactly 1, 2, 3, 4, 5, 6, 7. I'm using n pieces. It's just when I draw it, I have to make a choice about how many pieces I show. Okay. All right, so I've chopped this up into a bunch of pieces, all of which have the same width. Okay, excellent. Now, if they didn't have the same width, what I would have to do is use a subscript. So I'm going to need one anyway in order to talk about which subinterval I'm in. So I'm going to introduce a variable. Let's see. So if I have n is the number of pieces into which I chop the interval from A to B. That's a variable in the sense that it's a letter standing for a number, but it's not a variable in the sense that it's actually varying. It's fixed for this problem. Okay. So I might sometimes chop things into 15 pieces, in which case n would be 15. Other times I might chop things into 20 pieces, in which case n would be 20. But for any one time that I chop this up, I'm only chopping it up into some fixed number of pieces. So n is representing a fixed but unspecified number. I'm going to let I be my index. Now that's not the imaginary number I. We're working completely in the real numbers here. I'm using I just because the word index starts with that. And this is going to be a variable taking on integer values from 1 to n. That way I can talk about the ith piece. So if I wanted to talk about this third piece here, I would be 3. If I want to talk about the 18th piece, I would be 18. So I is my index. It just tells me which of the pieces I'm talking about. If I were not using a regular partition, then instead of having delta x being the width of each piece, I would have delta x sub I being the width of the ith piece. That just gets messier, so it's kind of nice to go ahead and use a regular partition. Okay, so that is step 1. We basically said, I want to find this area, and we turned it from one big problem into n littler problems. I want to now try to find the area of each one of these little strips of area, and then I'll add those all up, and that'll approximate the area that I'm looking for. Okay, we've got more to do, but we'll pick up with step 2 in the next video.